All right, so for today's lesson, we're going to finish up 2.3, going to get into 2.4 a little bit, although we've already talked a little bit about 2.4. So mostly it's going to be some examples today. So in 2.3, we did the limit laws. And so today what I want to do is do some example problems for you. So for instance, this guy here, the limit as x approaches 1/2 of 4x minus 1 times 2x minus 7. First of all, that's going to be, if you FOIL that out, that's going to be a polynomial. Yes? It's quadratic. So you know this thing has a limit. Why does it have a limit? Because it's continuous everywhere. But that's not what the question asks. The question says, hey, I want you to show me using limit laws how you do this. So remember, the limit of the product is the product of the limits. What this does is you're just practicing how these things work. So go ahead and break it up. And then you're like, wait, but Groom, the limit of the sum is the sum of the limits. You are correct. Do you hate us? Is this why you're making us do this? Well, yes, you're correct. That's exactly why I'm doing it. Good job. Exactly. No, you're totally right, actually. It's exactly why I hate you. Anyway, so whatever. No, it's actually good for you to be able to practice with the limit laws. Because what you'll end up doing is you'll end up seeing, oh, I can do that later on. But if you don't practice it, you'll be like, oh, I didn't know how I'm going to figure this limit out. Okay, so here it is. So, wait a minute, what about this 4? Bro, you can pull it out front. All right, sweet. Bro, what is the limit as x approaches 1/2? It's a half. It's a half times 4. That's hot. Now, what is the limit of 1? Well, 1 doesn't change, bro. So exactly. So minus 1. This one here, what is the limit as x approaches a half? Well, it's a half times 2 is 1. And what is the limit of 7? Last I checked, it is 7. And so that is going to be 2 minus 1 is 1. This is negative 6. Lo and behold, it's negative 6. Now, if you didn't believe me, and you're like, Groom, can we FOIL it out? Of course you can FOIL it out. So that's 8x squared minus 28 minus 30x plus 7. What happens if you put a half into there? So if you do 8, you get, that's a quarter, and that's 2. Half of 30 is 15. And negative 15 plus 9 is negative 6. It checks. You see that? So it's a different way of doing it. Obviously, the one we did previously, because it is continuous. Hey, we're gooch. And it wasn't a big deal there. Now, what about this fella here? The limit as w approaches 7 of the square root of w plus 2 minus 1. Oh, plus 1, sorry. And the squirt of w menos 3 es 3 c minus 1. Oh, that's hot. Okay, so again, the limit of the quotient is the quotient of the limits, as long as what? As long as the limit of the denominator is not what? Is not 0. 7 minus 3 is what? Well, it's 4. Square root of 4 is 2. 2 minus 1 is 1. We're gooch. I'm going to go ahead and do it this way and bring the limit up on the top. So the limit is w approaches 7 of the square root of w plus 2 plus 1. Take the limit of the whole numerator. Groom, could I have just multiplied? Could I just put that with both of them? I could have, but I'm going to do it this way if you don't mind. Don't tell me what to do, bro. Now, if you distribute that out, okay, well, what do you know? The limit of the sum is the sum of the limits. That's true, but we also know that the square root of the limit of the square root is the limit of the square root, like this, of w plus the limit as w approaches 7 of 2 minus the limit as w approaches 7 of 1 over the square root of the limit as w approaches 7 of w minus the limit as w approaches 7 of 3 minus, well, that top one's plus 1, minus 1, well, minus the limit approaches 7 of 1. Okay, so here we go. So what is the limit as w approaches 7? It's 7. What's the limit of 2? It's 2. What's the limit of 1? It's 1 over the downstairs. The limit as w approaches 7 is 7. The limit of 3 is always 3. 7 minus 3 is 4. So, and then minus the limit, yeah, it's 1. And so that's 9. Square root of 9 is 3. 3 plus 1 is 4. 2 minus 1 is 1. The answer is 4. Okay? And again, we're just getting used to using the limit laws. Okay? That's what makes these kind of cool. Right now, a couple of oh, Judas Priest, my book's cold. That's cold. Ouch. That's cold. Okay. Yeah, I think we're good there. So that is most of section 2.3 that we didn't talk about the other day. We wrote the limits down, but we didn't actually practice with them. Now, 2.4 is about continuity. So if you recall, continuity. Come on, here we go. So continuity, yes, we say something is continuous at the point. What did we talk about that? So we said that for a function to be continuous, for a function to be continuous at x equals c, first of all, f of c must exist. We say the limit as x approaches c must exist. 1, this is 2. In other words, 1 and 2 must equal each other. In other words, the limit as x approaches c of f of x must equal f of c. That's what continuity. You with me? And remember, this is an if and only if statement. If I show these three things to be true, it's continuous. If I told you it's continuous, those three things are true. Okay? Pretty sweet, pretty big deal. Kind of a big deal, honestly, going forward. Okay. Now, if we think about this, we talked about the functions that are continuous. We talked about polynomials. We talked about linear, sine, cosine, e to the x, whatever, right? We also talked about like log of x is continuous. We can say on its domain. And what is its domain? Well, x bigger than 0. Okay. Now what happens at 0? Well, at 0, it's not truly continuous. So we say it is right continuous at x equals 0 because it's continuous from the right. Yes? We say it's right continuous all the way down to 0. Okay, at 0 we got a problem. Can't have 0, but all the way down to 0. Okay. Those are all pretty easy ones. Stuff we've talked about stuff we talked about the other day. But what I want to get into today is take it a little bit step deeper. Gonna see what's up here. Okay. And some questions like this we're gonna pop up today. Okay. For instance, this guy right here. All right. So number 8. Number 8 says this, x sine x. So this right here is your function. And the question is it continuous, yay or nay? Now, it wants you to use the laws of continuity, and it wants you to use theorems 2 and 3 to show the function's continuous. So if you flip back, so theorem 2 says that if you have a polynomial and a rational function, okay, polynomials, we say are continuous everywhere, yes? That's a fact, Jack. Also, theorem 3 says sine of x is continuous. That's hot everywhere. Beautiful. Now, the question then is, okay, well, what about continuity? Okay, well, it also says this. If you have two continuous functions, f of x times g of x, if he's continuous and you multiply it by another continuous function, you get some other function which is, wait for it, continuous. So is this guy continuous? Sure is. Is this guy continuous? Sure is. If I multiply them, will I get a continuous function? Check. I want you, when you're doing these problems, to phrase it out, okay? Because this, and this, therefore it has to be continuous. How about this cat? Number 10 here, it says 3x cubed plus 8x squared minus 20x. How do I know it's continuous? It's a polynomial. Check. Okay, next. Okay, what about this cat? F of x is equal to 3. No, it's not. It's equal to, no, poop. It's equal to x squared minus cosine x divided by 3 plus cosine x. Is it continuous? Well, let's start with the numerator. Is the numerator continuous? Well, it turns out if you have f of x, it's continuous, and you either add or subtract g of x, which is also continuous, the sum or difference will always be continuous. Yay! X squared, polynomial, continuous. Cosine, continuous. Continuous minus continuous is, wait for it, that's right, continuous. That's hot, okay? But about the bottom, well, 3 technically is part of a polynomial, but it's also linear, so whatever you want to call it. That's continuous, plus cosine, also continuous. Hey, we're gooch. Now, that is, of course, theorems, as I said, 2 and 3. Now, part of 2 said this. If you have p of x divided by q of x, okay, and he's continuous, and he's continuous, this guy is continuous everywhere. It's continuous as long as what? Q of x does not equal 0. Okay? If q of x equals 0, which, by the way, it cannot, because what is cosine? Cosine bounces up and down between -1 and +1. So the denominator is going to be somewhere between 2 and 4 always, yes? Well, it's not 0, so we are gooch. This guy is always continuous. Always, always. Always, always. Okay? The ln of x to the 4th plus 1. You're like, whoa, hold on. This is f of g of x. Hey, that's a composite function. I wonder if there's a theorem about that. Well, you know what? Turns out there is. If you look back to theorem 5, it says this. If g, so we have f of g, you with me? We have f of g of x. If g is continuous at x equals c, and f is continuous at x equals g of c, then f of g of x is continuous at x equals c. Now, what do I mean by that? Well, here's this. This guy here, is he continuous? By God, he is continuous. Yes, anything you put in there, you will get a number bigger than or equal to 1, no matter what you do. Yes? That's interesting. That is now inside of the ln function. Well, now, what do we know? We know that ln, x had better be bigger than 1. So, but listen, we don't have x anymore. We have g of x. So in other words, g of x better be bigger than 1. Bigger than or equal to. Bigger than or equal to 1. Yeah, bigger than. Well, sorry. Let me back that up. Let me back that up here. Let me back it up. It's an ln, so we know that x better be bigger than 0. Anything we put in here had better be bigger than 0, yes? Because you're doing an ln function, correct? Well, that's cool, because that guy in there, x to the 4th plus 1, is always bigger than or equal to 1, yes? Nice. So what does that mean? This satisfies the domain of ln of x, yes? Because now when I replace x with x to the fourth plus 1, okay, this guy here is never going to be 0. It's never going to be less than 0. So that means because it's this composite function, hey, this guy is continuous. And specifically, it's continuous everywhere. And if you don't believe me, let's go ask the computer. By the way, can I check myself? Of course you can check yourself. Okay, you have to be able to word these things out for me. But I do want you to be able to go, am I right? I don't know. Go look at the map. So if I do the ln of x to the 4 plus 1. Hey, bro, look at that. That baby's continuous everywhere. That's cool. Nice. And yeah, awesome. Okay, nice. Now on these next guys, it says determine the points of discontinuity. The points of discontinuity. Okay. What kind of discontinuity is it? So there are several types of discontinuity types. Okay, so first of all, obviously you could have an asymptote, right? Obviously. Vertical asymptote. You could have a hole. A hole is often referred to as a removable discontinuity. Okay, you could have a jump. Oh, by the way, your book refers to this as an infinite discontinuity because it goes to infinity, right? Okay, well, that's exciting. So if I have this guy here, so f of x equals the greatest integer function. Groom, I don't remember what that looks like. Let's go ask Betsy. She'll remember. Betsy always knows. Also referred to as a floor function. Floor x. Boop. Oh boy. Oh boy. Oh boy. So we say it has discontinuities. X equals integers, yes? Okay, any of the integers, you got a problem. What kind is it? It's a jump discontinuity. Okay. What about this cat? So it is some piecewise function, cosine of 1 over x, x not 0, and 1 when x is equal to 0. Okay, I got to graph this pig. Okay, but look at that. I zoom in, zoom in, and zoom in. No matter what I do, the thing's going to keep oscillating, yes? So what is that thing? That is a discontinuity. Now, what kind of discontinuity is it? Okay, well, is it a jump? Well, it's not a jump. It's not a jump. But what's going to be happening, these lines are going to be going more and more vertical, yes? So what's going to be happening is that's actually going to be an infinite discontinuity. Okay, it's kind of weird because you expected an asymptote, but technically that's an infinite one. G of t equals 3t to the minus 2/3 minus 9t cubed. Now this fellow here, we're Gucci on him. This guy is a little weird though. It's t to the 2/3. Uh-oh, what's the problem? Well, at 0, you're going to have a problem, right? Question, is it, and I don't know the answer because I don't know, I just work here. Is it a asymptote or what's going on there? I don't know. Let's find out. Oh, interesting. Oh boy, look at that. It's an asymptote, yes? It goes up to infinita. So it's an asymptote, or if you prefer, an infinite one. Okay? Pretty easy, pretty straightforward. What happens if you have this guy, ln of x minus 4? Okay, remember what we can't have in here is what? We can't have 0. Uh-oh. So at x equals 4, we're going to have a problem, yes? That's going to be a problem. But what is the problem? Okay, what is it? Is it going to have an infinite? Is it going to have an asymptote? Or is it going to be, you know, what's happening here? So again, you just look at it. Sometimes it's real obvious. Other times you're like, I need a graph. So I'm going to make a graph. Oops. Oh dear, it's an asymptote. Yes, it's an asymptote. Or again, if you prefer, it is a infinite discontinuity. Okay, cool. 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 So another part of this lesson is going to be something like this. So if you have x squared plus 9, what's the domain of this function? Well, x squared plus 9 needs to be bigger than or equal to 0. Well, it's always bigger than or equal to 0, so it's all reals. Okay, it's all reals. Okay, now think about that. That means I'm always going to get a positive number, yes? Right? So that means this is, you have a function, let's call it g of x, which is square root of x. And you've got some h of x, which is x squared plus 9. Look what you've got. You've got g of h of x, yes? Is equal to the square root of x squared plus 9, right? So we have to be careful. The square root function needs to be bigger than or equal to 0. We did that already, right? So is this function going to be continuous? Yes, because this guy in the middle always fits in the domain of the outside function, right? And it's a composite function. Okay, that's all you got to talk about. That's it. Okay. This one here might be fun. X squared over x plus x to the 1/4. Okay, so I see a division of I see a rational function, right? The top is continuous. The bottom is continuous everywhere, yes? Because x is continuous everywhere. And if you recall, bloop, that looks like that. So as long as x is bigger than or equal to 0, the bottom guy is continuous, yes? Right? But you're like, Groom, it can't be 0. Bro, I'm on it. Remember, though, we said that if you have p of x divided by q of x better not be 0. Well, when does that happen? It happens when x is equal to 0. So we would just simply say this. Ta-da! So because this is continuous on its domain, all we have to do then is tweak the bottom guy to make it not equal 0. So instead of being greater than or equal to 0, we just say it's just greater than 0. Yay! And the crowd goes wild. This one looks interesting. The ln of 9 minus x squared. That's a function in a function, yes? 9 minus x squared better be bigger than 0. So 9 better be bigger than x squared. So x had better be less than 3, or, by the way, negative 3. By the way, this looks ridiculous. Don't ever write it that way. We go from least to greatest. That function right there, we're gooch. Okay, as long as you don't equal 3, we're just fine. So x squared minus 9. Oops, I did it backwards. 9 minus x squared. Nice. So as long as we stay between there, we're Gucci, yes? Because it's a function in a function. You're like, but Jake, 9 minus x squared is what? Well, it's polynomial, so it's continuous everywhere. However, because it's inside of an ln, we just have to go, what's inside must be bigger than 0. And so we just restrict the domain to that. Make sense? And so you're just going to kind of talk yourself through that a little bit. Okay? I'm going to put in this piecewise function here. It's actually in your book. X squared plus 3. And then if you recall, maybe you don't, use these little squiggly brackets. And we're going to put in x less than 1. So that thing there. And then we're going to put in 10 minus x. And the squiggly brackets over here. that's hot. And then we're going to put in 6x minus x squared, squiggly brackets, x greater than 2. Nice. Nice. And so the question is simply this. What is the right-hand limit at x equals 1? Well, the right-hand limit, it looks like it's approaching 9. You with me? 9. Boom. Done. What's the left-hand limit at 1? Looks like it's approaching 4, yes? What is the limit at 1? It doesn't exist. What is the limit at x equals 2? Oh, Groom, it's undefined. Listen. Okay, let me back the train up here, friends. Is it undefined? Yeah, it's undefined. However, coming from this side, undefined. Coming from this side, it's, boom, 8, yes? But the limit is 8 because on both sides we are approaching 8, yes? Is the function continuous at x equals 2? It sure is. When you're at x equals 2, you're on the green function. Does that make sense? But notice that when you plug in 2 into this guy, you're going to get 12 minus 4 is also 8, isn't it? Right? But we can only be using one or the other of these guys. So right there, is it continuous? It sure is continuous. And the right-hand limit is equal to the left-hand limit. Okay? How exciting for us. By the way, this guy here does not exist at 4. Do you see that? Undefined. Well, it's undefined when you get there. Or 2 is undefined. Anyway, it's undefined because we're not equal to 1 up here. You see that? We're not equal to it. And so it's undefined. But does that mean the limit is undefined? No, the limit is absolutely defined. Are you with me? It's absolutely defined. The limit is, we're gooch. The problem is simply a matter of the limit from the left is equal to 4. The limit from the right is equal to 9. Okay, so the limit doesn't exist. Okay, you're going to be sketching a few of these guys. I do it exactly like I did it. Problems like 51 through 54. Exactly the same way. Okay. Last couple I want to do here just for fun is this. If I ask you to find the limit as x approaches 2 of 5x minus 12x to the minus 2, which of course is the same thing as saying the limit as x approaches 2 of 5x minus 12 over x squared, okay, is this guy continuous? 5x. Sure is. Is this guy continuous at 2? In other words, you put 2 in, you're going to get over 0. No. So they're both continuous. So this is a continuous function, and this is a continuous function. We know that the limit as x approaches c of f of x is equal to f of c because it's continuous. So me and Goom, all I have to do is substitute. That's what I was trying to say without saying it. That's correct. That's your limit right there. Okay, I can do that because they're continuous functions. Okay, here's another example of that, and then I'll just shut up and let you get your work done here. So suppose I said, hey, let's take the limit as x approaches pi of 1 over cosine x. Okay. Well, that's cute. Is this continuous? It is. Is this continuous? Yes, as long as the cosine of whatever you're thinking about doesn't equal 0. Well, what's the cosine of pi? Well, it turns out the cosine of pi is -1. So in other words, it's going to be, so we're good. So it's going to be 1 divided by -1. The answer is -1. Okay? That easy. Because again, continuous. Notice if we said this, that's problematic. Yeah, oh, I lied to you. Sorry. This, oh, don't go to sleep, you piece of crap. If I asked you this question, we'd be screwed, right? Because the cosine of pi over 2 would be 0. So that's no good, yes? So because it's at pi, we're Gucci, okay? So that is 2.3 and 2.4. That should give you plenty of stuff to work on to get you going there, okay? And on Monday, we'll kind of pick back up and see where we're at, okay? Have a good weekend.